Space doesn't have a temperature. That statement probably sounds wrong, maybe even ridiculous, but it's technically true. And understanding why reveals something far stranger about the universe than most people realize. You've heard space described as cold, freezing, deadly. Movies show astronauts instantly turning into frozen statues the moment their suits breach. But here's what nobody tells you. The vacuum of space isn't cold in the way you think. Temperature measures how fast particles move. And in the near-perfect vacuum of space, there aren't enough particles to have a temperature at all. So when we talk about how cold space is, we're really talking about something else entirely. The baseline everyone quotes is 2.7 Kelvin. That's negative 270 degrees Celsius, or negative 455 Fahrenheit if you prefer. Just 2.725 degrees above absolute zero, the theoretical point where all atomic motion stops. This temperature comes from the cosmic microwave background radiation, the leftover glow from the Big Bang itself. It's ancient light that's been traveling for nearly 14 billion years, stretched by the expansion of the universe until it became this faint microwave whisper that fills every cubic centimeter of space. But that number, 2.7 Kelvin, doesn't tell you what would actually happen to you out there. Picture yourself floating outside the International Space Station. No suit, no protection. What happens next? If you're imagining instant freezing, your body crystallizing in seconds like some morbid ice sculpture, you're wrong. Dead wrong, ironically. The reality is far more complex and considerably more disturbing than simple freezing. Your body wouldn't freeze, not quickly anyway. In fact, overheating would be a bigger immediate concern than cold, which seems completely backwards until you understand how heat actually works in a vacuum. On Earth, when you get cold, your body loses heat through three mechanisms: conduction, convection, and radiation. Touch something cold, and conduction transfers your heat directly to that object. Stand in cold air, and convection carries your warmth away as air currents move past your skin. But in space, two of these three mechanisms simply don't exist. There's nothing to touch, no air to create convection. You can only lose heat through radiation, which is catastrophically slow. Your body generates about 100 watts of heat just existing, and in the vacuum of space, that heat has nowhere to go except slowly radiating away as infrared light. It would take somewhere between 12 and 26 hours for your body to freeze solid, depending on exactly which region of space you're drifting through. You'd be long dead by then, but not from the cold. Oxygen deprivation kills you first. Within 15 seconds, deoxygenated blood reaches your brain and consciousness fades. But here's where it gets genuinely horrifying. You wouldn't suffocate in the way you'd suffocate underwater, desperately holding your breath until your lungs burn. If you tried to hold your breath in space, your lungs would rupture. The air inside them, no longer compressed by external atmospheric pressure, would expand violently. You'd have to exhale, releasing that breath into the void where it would immediately boil away. Yes, boil. Because in the near vacuum of space, water's boiling point drops to match your body temperature. The moisture on your tongue, in your mouth, lining your airways, all of it would start boiling. Not from heat, but from the absence of pressure. This process, called Ebism, causes your soft tissues to swell grotesquely as water vapor forms under your skin. Your body would inflate like some twisted balloon, though your skin is actually strong enough to prevent you from bursting. Your eyes wouldn't explode either, despite what the movies show, but they'd certainly suffer damage. Meanwhile, dissolved gases in your bloodstream would form bubbles, like a diver ascending too quickly from depth. These bubbles would race through your circulatory system, blocking blood flow, stopping your heart within about a minute. You'd lose consciousness in 15 seconds and be dead within 90. But those 90 seconds would be among the most unpleasant in human experience. The temperature wouldn't even register as a problem. This disconnect between what we expect and what actually happens reveals something crucial about space itself. When we say space is cold, we're imposing our Earth-based understanding onto an environment that operates by completely different rules. The cosmic microwave background gives space a baseline temperature of 2.7 Kelvin, sure, but that's measuring the energy of photons floating through the void, not the temperature of matter the way we normally think about it. And here's where things get really strange. Space isn't uniformly that temperature anyway. Not even close. Step out of the ISS into direct sunlight and you're exposed to solar radiation that can heat surfaces to 250 degrees Fahrenheit, hot enough to boil water, drift into shadow, and temperatures plummet to negative 250 degrees Fahrenheit within moments. The same object in the same location can have a 500-degree temperature difference between its sunlit and shadowed sides, separated by mere inches. The Moon experiences exactly this. Its equator reaches 250 degrees Fahrenheit during lunar day, then drops to negative 300 degrees Fahrenheit during lunar night. A 550-degree swing with no atmosphere to moderate the extremes. Mercury has it even worse. Closest to the Sun, its day side bakes at temperatures that can melt lead, while its night side drops to 95 Kelvin, negative 288 Fahrenheit. These aren't exotic locations in deep space. These are our closest celestial neighbors, experiencing temperature variations that would be impossible on Earth because we have an atmosphere that redistributes heat, preventing such wild fluctuations. Near Earth orbit, where thousands of satellites and the ISS circle our planet, the average temperature sits around 50 degrees Fahrenheit. Room temperature, essentially. But that average is meaningless because it masks the reality of rapid oscillation between extreme heat and extreme cold, as objects move in and out of Earth's shadow every 90 minutes. The ISS exterior ranges from -4 to +45 degrees Celsius on average, but the sun-facing side can spike to 260 degrees Celsius, while the shadow side simultaneously drops to -100. Managing these extremes is one of the most challenging aspects of spacecraft engineering. You can't use convection or conduction to move heat around because there's no air, nothing to touch. Everything must be handled through radiation, reflection, and active cooling systems. The ISS has massive radiator panels that glow with waste heat, dumping excess thermal energy into space as infrared radiation. Without them, the station's interior would quickly become uninhabitable, cooked by its own systems and the sun's relentless radiation. This is why spacesuits are engineering marvels. They have to protect astronauts from a 500-degree temperature range, from -250 degrees Fahrenheit in shadow to +250 degrees Fahrenheit in direct sun. Modern suits use 14 different layers, each with a specific purpose. 7 layers of aluminized mylar insulation work like a thermos, maintaining consistent temperature regardless of external conditions. The outermost layer, made from a blend of Gore-Tex, Kevlar, and Nomex, can withstand temperatures from -300 to +300 degrees Fahrenheit. But even these layers aren't enough. Astronauts wear a liquid cooling and ventilation garment against their skin, essentially a network of tubes carrying chilled water that removes body heat and dumps it into space through external radiators. Without active cooling, the insulation that protects astronauts from space's temperature extremes would cause them to overheat from their own body heat within minutes. The engineering gets more sophisticated when you move beyond Earth orbit. Deeper into space, away from the sun's warming radiation, temperatures drop closer to that 2.7 Kelvin baseline. The coldest naturally occurring places we've found are molecular clouds, regions of dense gas in interstellar space where new stars are born. These clouds can reach as low as 10 Kelvin, just 10 degrees above absolute zero. At these temperatures, hydrogen atoms move so slowly they barely qualify as gas anymore. But there's one place that defies even this. One location in the observable universe that's colder than the cosmic microwave background itself, colder than the ambient temperature of space, colder than anywhere else we've ever detected. The Boomerang Nebula, located 5,000 light-years away in the constellation Centaurus, measures 1 Kelvin, 1 degree above absolute zero. That's colder than the 2.7 Kelvin background radiation, which seems impossible. How can something be colder than the temperature of space itself? The answer lies in a dying star at the nebula's center. This star is expelling gas at phenomenal speeds, over 100 miles per second, losing mass at a rate 100 times faster than typical dying stars. As this gas expands outward, it cools through a process called adiabatic expansion. The gas does work pushing against itself, which removes energy from the system, dropping its temperature. The Boomerang Nebula is essentially a cosmic refrigerator, actively pumping heat out faster than radiation from surrounding space can warm it back up. This creates a region where the nebula is actually absorbing heat from the cosmic microwave background. The universe's ambient radiation is warming the Boomerang Nebula, not the other way around. It's the only place we know of where this happens naturally. Scientists have created colder temperatures in laboratories on Earth, getting within billionths of a degree of absolute zero using laser cooling and magnetic traps. But in nature, across the entire observable universe, nothing is colder than the Boomerang Nebula. These extremes, from the boiling radiation near stars to the near absolute zero temperatures of molecular clouds and dying stellar remnants, reveal just how varied space actually is. The simple answer of 2.7 Kelvin doesn't capture this complexity. Space isn't uniformly cold, it's a patchwork of extreme temperatures, each region shaped by its proximity to stars, its density of matter, and the complex physics of radiation and expansion. And we haven't even touched on the hottest regions yet. Because while space can be unimaginably cold, it can also be unimaginably hot in ways that challenge everything we think we know about temperature itself. The plasma between galaxies, for instance, reaches temperatures of millions of degrees Kelvin. This isn't a typo. Millions. The intergalactic medium, the diffuse gas that fills the space between galaxies, is heated by gravitational forces and shock waves from galactic collisions. Recent measurements show temperatures around 2 million Kelvin near cosmic structures. This gas is so hot that atoms can't exist in it. Electrons are stripped from nuclei, creating a plasma where particles move at incredible speeds. How can something be millions of degrees hot while the cosmic microwave background is 2.7 Kelvin? Both exist in the same space, simultaneously. This seems contradictory until you remember that temperature in space doesn't work like temperature on Earth. The hot plasma is incredibly diffuse, less than 1 hydrogen atom per cubic meter in most regions. The cosmic microwave background photons are far more numerous, roughly 400 per cubic centimeter. They coexist because they barely interact. The plasma particles are moving at extreme speeds, but they're so sparse that they rarely collide with anything. This is the fundamental weirdness of space temperature. On Earth, hot and cold mix. Air currents blend them, conduction equalizes them. But in space's vacuum, hot and cold can exist side by side, separated by nothing but emptiness, never reaching equilibrium because there's nothing to transfer the heat between them. Understanding this changes how we think about space exploration. It's not just about building ships that can withstand cold. It's about managing thermal extremes that don't exist on Earth, protecting against radiation that can heat surfaces to boiling while simultaneously radiating into a void that's barely above absolute zero. It's about recognizing that temperature itself behaves differently when there's nothing to carry it. The truth about how cold space really is turns out to be far more complex than a single number. It's a story about the nature of temperature itself, about how heat moves or doesn't move through emptiness, about the strange physics that governs the void between stars. And as we'll see, this is just the beginning of understanding what space's temperature really means for everything from the smallest particles to the fate of the universe itself. This coexistence of extremes reveals something counterintuitive about thermal dynamics in the void. The intergalactic medium, that diffuse soup of particles between galaxies, holds temperatures exceeding 2 million Kelvin in some regions. These particles race through space at velocities that would vaporize anything they touched. Yet they're surrounded by the 2.7 Kelvin cosmic microwave background. Both temperatures exist in the same location, neither cancelling the other out, like two radio stations broadcasting on different frequencies through the same airspace. Why doesn't the hot plasma heat up the cold background radiation? The answer lies in particle density. That million-degree plasma contains less than 1 hydrogen atom per cubic meter. The cosmic microwave background, meanwhile, bathes every cubic centimeter in roughly 400 photons. The plasma particles are moving incredibly fast, which is what gives them their high temperature. But they're so sparse, they rarely interact with anything. Temperature measures average kinetic energy of particles, but in space's vacuum, having high kinetic energy doesn't mean you can transfer much heat. There's simply nothing to transfer it to. Recent observations have complicated this picture further. Research from Ohio State University's Center for Cosmology and Particle Physics discovered that this intergalactic plasma is actually getting hotter over time. The universe, despite its overall expansion and cooling, is seeing its gas content increase in temperature. This seems paradoxical until you consider the mechanisms at work. Galaxies aren't static. They move, collide, merge. These interactions create shock waves in the intergalactic medium, heating the gas to millions of degrees. Supermassive black holes at galactic centers pump enormous amounts of energy into surrounding space. Stars explode, ejecting material at a significant fraction of light speed. All of this activity injects energy into the thin gas between galaxies, gradually raising its temperature even as the universe expands. This means space is simultaneously cooling and heating. The cosmic microwave background temperature decreases as the universe expands, stretched by the increasing distance between galaxies. But the matter in space, sparse as it is, grows hotter through gravitational and energetic processes. Both trends are real, both are measurable, and both shape the thermal landscape of the cosmos. Near-Earth orbit presents entirely different thermal challenges. The International Space Station experiences temperature swings that would destroy most terrestrial structures. The sunward side can reach 260 degrees Celsius, while the shadowed side plunges to -100 degrees Celsius. These extremes exist simultaneously, separated by mere meters. An astronaut performing a spacewalk might have one hand in scorching heat and the other in frigid cold. This isn't because space itself is hot on one side and cold on the other. The vacuum surrounding the ISS maintains that baseline 2.7 Kelvin temperature everywhere. What changes is direct exposure to solar radiation versus its absence. The sun bombards the station with electromagnetic energy, heating any surface it touches. But the moment that surface rotates into shadow, with no atmosphere to retain warmth, it begins radiating heat away into the void. The station orbits Earth every 90 minutes. This means temperature cycles repeat 16 times per day. Materials expand and contract. Metal groans. Joints stress. Engineers designing spacecraft must account for these thermal oscillations, selecting materials that can withstand thousands of heating-cooling cycles without degrading. It's not enough to handle extreme temperatures. They must handle extreme transitions between those temperatures, repeatedly, indefinitely. Mercury provides a planetary-scale example of these dynamics. As the closest planet to the Sun, it receives 7 times more solar energy per square meter than Earth. Daytime temperatures on Mercury soar to 430 degrees Celsius, hot enough to melt lead. But Mercury has essentially no atmosphere, just trace amounts of gas captured temporarily from the solar wind. Without atmospheric insulation, nighttime temperatures plummet to -180 degrees Celsius. This 610-degree swing between day and night exceeds what any other planet experiences. Mercury's surface alternates between a searing hellscape and a frozen wasteland every 176 Earth days, which is how long it takes Mercury to complete one day-night cycle. The Terminator, that boundary between day and night, moves across the surface like a slow wave of thermal devastation. Rocks expand in the heat, crack in the cold, gradually pulverizing themselves over millions of years. The Moon demonstrates similar extremes, though less severe. Lunar day temperatures reach 127 degrees Celsius in direct sunlight at the equator. Lunar night temperatures drop to -173 degrees Celsius. This 300-degree range occurs because the Moon, like Mercury, lacks atmospheric insulation. Heat arrives through radiation from the Sun, and heat leaves through radiation into space. Nothing moderates these exchanges. But here's what makes the Moon's thermal environment particularly interesting for understanding space temperature. The lunar regolith, that layer of powdered rock and dust covering the surface, acts as an insulator. Just below the surface, temperatures remain relatively stable, hovering around -20 degrees Celsius, regardless of whether the surface above is baking or freezing. This happens because the regolith conducts heat poorly. The vacuum between individual dust grains creates tiny insulating pockets. This principle, vacuum as insulation, explains why spacesuits work. The challenge isn't just keeping astronauts warm, it's managing heat in an environment where heat can only transfer through radiation. Human bodies generate approximately 100 watts of heat through metabolism. In Earth's atmosphere, this heat dissipates easily through convection and conduction. In space's vacuum, that same heat has nowhere to go except through radiation, which happens slowly. Modern space suits include active cooling systems precisely because overheating poses a greater threat than freezing. The liquid cooling and ventilation garment worn directly against the skin circulates chilled water through a network of tubes. This water absorbs body heat, then flows to an external radiator where it releases that heat into space through thermal radiation. Without this system, an astronaut would overheat within minutes, even in the coldness of space. The suit's outer layers serve multiple purposes. 7 layers of aluminized mylar insulation reflect radiation, preventing excessive heat gain from the sun and excessive heat loss into shadow. The outermost layer, a blend of Gore-Tex, Kevlar and Nomex, can withstand temperatures from -180 degrees Celsius to 150 degrees Celsius. But even this remarkable material doesn't experience those extremes simultaneously because the vacuum between layers prevents rapid heat transfer. This multi-layer approach mimics how a thermos bottle works. The vacuum between layers blocks conduction and convection. Reflective surfaces minimize radiation. The result is a system that maintains stable internal temperatures despite wild external variations. It's not fighting against space's temperature. It's leveraging the physics of vacuum to create controlled thermal isolation. What would actually happen to an unprotected human in space? Hollywood has created persistent myths about instant freezing or explosive decompression. The reality, while still fatal, unfolds differently. You wouldn't freeze instantly because freezing requires heat transfer, and heat transfer in vacuum happens slowly. You wouldn't explode because human skin is surprisingly strong, capable of containing internal pressure even in vacuum. The actual sequence of events is both less dramatic and more unsettling. Within seconds, the water on your tongue and in your eyes would begin to boil. Not because space is hot, but because water's boiling point depends on pressure. At the low pressures of space, water boils even at body temperature. This causes rapid evaporative cooling of exposed tissues, but not full body freezing. Simultaneously, dissolved gases in your bloodstream would form bubbles, a condition called Ebism. These bubbles would swell your body, though skin elasticity would prevent actual rupture. The real killer would be oxygen deprivation. After 15 seconds, deoxygenated blood would reach your brain, causing unconsciousness. After 90 seconds, the damage would likely be irreversible. Throughout this entire process, your core body temperature would drop slowly. Estimates suggest 12 to 26 hours before a body would freeze solid in space, depending on local conditions. This seems impossible given space's extreme cold, but it demonstrates how inefficient radiative heat transfer is without conduction or convection to assist it. There's documented evidence supporting this timeline. In 1966, a technician at NASA Houston experienced accidental decompression in a spacesuit test chamber. He remained conscious for about 14 seconds, and later recalled feeling the saliva on his tongue begin to boil. He survived because the chamber was repressurized within 30 seconds. His account provides rare first-hand testimony of what vacuum exposure actually feels like. Animal studies corroborate these findings. Dogs exposed to near-vacuum conditions for up to 90 seconds showed complete recovery with no lasting effects. Chimpanzees survived exposures of up to 3.5 minutes and performed complex cognitive tasks normally months later. These experiments, while ethically questionable by modern standards, establish that vacuum exposure is survivable for brief periods, contrary to popular belief. The only humans known to have died from vacuum exposure in space were the 3 cosmonauts aboard Soyuz 11 in 1971. A valve malfunction during re-entry caused their capsule to depressurize while still in space. By the time the capsule landed and ground crews opened it, all 3 were dead. They were found in positions suggesting peaceful loss of consciousness rather than violent trauma. Understanding these realities changes how we think about space exploration risks. Temperature extremes matter, but they're manageable with proper equipment. Pressure loss is immediately life-threatening, but not instantly fatal. Radiation poses long-term cancer risks. Microgravity causes bone density loss and muscle atrophy. The actual hazards of space are more nuanced than simple narratives of cold or heat would suggest. This nuance extends to how spacecraft manage thermal loads. The challenge isn't just maintaining comfortable internal temperatures. It's dealing with heat that has nowhere to go. Every electronic system generates waste heat. Solar panels collect energy, but also heat. Mechanical systems produce friction. In Earth's atmosphere, this heat would dissipate naturally. In space, it accumulates. Spacecraft use radiators, large panels designed to maximize surface area exposed to space. These radiators reject heat through thermal radiation, the only mechanism available. The Space Shuttle had radiators in its cargo bay doors. The ISS has massive radiator arrays that dwarf its solar panels. Satellites orient themselves to keep sensitive equipment shaded while ensuring radiators face deep space. But even with radiators, thermal management requires constant attention. Spacecraft must balance heat absorption from the sun against heat rejection into space. Too much absorption causes overheating. Too much rejection causes freezing. This balance shifts depending on orbital position, solar activity, and operational demands. Computers constantly adjust louvers, rotate radiator panels, and redirect fluid flows to maintain equilibrium. The physics underlying these engineering challenges reveals something profound about space itself. Temperature, as we experience it on Earth, depends on molecular collisions transferring kinetic energy. In space's vacuum, molecules are so sparse that collisions rarely occur. This means temperature becomes a less useful concept. A single molecule moving at high velocity has high kinetic energy, which we call temperature. But if it never collides with anything, that energy remains locked in that single particle, unable to heat anything else. This is why the intergalactic medium can be millions of degrees, yet pose no threat to a spacecraft passing through it. The particles are moving fast, but they're so far apart they'd rarely hit anything. A spacecraft might encounter a few hundred particles per second, each depositing a tiny amount of energy. Meanwhile, the spacecraft radiates away orders of magnitude more energy through its own thermal radiation. Space's temperature is thus context-dependent. The cosmic microwave background provides a baseline of 2.7 Kelvin. Local matter, if present, might have temperatures ranging from 10 Kelvin in molecular clouds to millions of Kelvin in galactic plasmas. Solar radiation creates temperature differentials based on exposure, but none of these temperatures behave like temperatures on Earth because the mechanisms of heat transfer are fundamentally different. What does this mean for the future of space exploration? It means we're not just learning to survive in cold. We're learning to operate in an environment where temperature itself works differently, where heat and cold can coexist without mixing, where the normal rules of thermodynamics still apply but manifest in unfamiliar ways. This environment demands adaptations we're only beginning to understand. Consider the International Space Station's thermal control system. It's not designed around a single temperature challenge. It's designed around dozens of simultaneous, often contradictory requirements. Electronics need cooling. Crew needs warmth. Experiments require precise temperature ranges. Solar panels generate heat while producing power. Life support systems create thermal loads. Every watt of electrical power eventually becomes waste heat. The station uses ammonia loops, massive systems that circulate refrigerant through internal heat exchangers, then pump it to external radiators. These radiators are enormous. The ISS has radiators totaling over 3,000 square feet. They glow faintly in infrared cameras, visible signatures of heat being dumped into space's void. But even this isn't straightforward. Radiators work through Stefan Boltzmann law, emitting energy proportional to the fourth power of temperature. Small temperature changes create large emission differences. Managing this requires constant adjustment. The station must also contend with orbital mechanics affecting thermal loads. In sunlight, solar input is roughly 1,400 watts per square meter. In shadow, it drops to nearly nothing. The ISS orbits Earth every 90 minutes, creating 16 sunrises and sunsets per day. Each transition represents a thermal shock. Materials expand in heat, contract in cold. Over time, this cycling creates metal fatigue, seal degradation, structural stress. Engineers design for this, but it remains an ongoing challenge. Now shift perspective to deeper space. Beyond Earth's orbit, solar intensity drops according to the inverse square law. At Mars, it's less than half Earth's intensity. At Jupiter, it's 25 times weaker. At Neptune, it's nearly 900 times weaker. This changes everything about thermal management. Spacecraft that far from the Sun can't rely on solar heat. They need internal heating systems, often radioisotope thermoelectric generators that convert radioactive decay into electricity and heat. Voyager spacecraft, launched in 1977, still function partly because their RTGs continue providing warmth alongside power. But what about truly interstellar space? The regions between star systems. Here, the cosmic microwave background becomes the only baseline. No nearby star provides radiation. No planets reflect sunlight. The temperature approaches that 2.7 Kelvin floor asymptotically. Objects would slowly radiate away their heat until reaching equilibrium with the CMB. For a spacecraft, this would take considerable time. Metal and plastic have thermal mass. They store heat energy. Radiating that away in vacuum is slow. A spacecraft entering interstellar space wouldn't instantly freeze. It would cool gradually over days or weeks, depending on its construction. This raises questions about interstellar travel. Any civilization attempting it must solve the temperature problem differently than we solve it for Earth orbit. You can't use solar panels for power. You can't use solar heating for warmth. You need either onboard power sources like fusion or fission reactors, or you need to harness other energy forms. Some proposals suggest using cosmic rays, high-energy particles constantly streaming through space. Others propose magnetic sails that interact with interstellar medium. But all must contend with the fundamental issue. Space at this distance is cold, dark, and indifferent. The Boomerang Nebula illustrates how strange temperature can become in unusual conditions. This planetary nebula, 5,000 light-years distant, holds the record for coldest known natural object. Its temperature, 1 Kelvin. That's colder than the cosmic microwave background. How is this possible? The dying star at its center expelled gas at phenomenal speed, over 100 miles per second. This rapid expansion creates adiabatic cooling, where gas doing work against its own pressure loses internal energy. The expansion is so violent and so fast that the gas cools below the temperature of surrounding space. It's actively absorbing heat from the CMB, warming up toward 2.7 Kelvin. In a sense, the Boomerang Nebula is the universe's refrigerator, a natural cooling system more efficient than the background radiation itself. This phenomenon isn't just cosmic curiosity. It demonstrates principles relevant to spacecraft design. Adiabatic expansion cools gases. Compressed gases, when released, drop in temperature. This is how refrigerators work on Earth. In space, you could theoretically use similar principles for cooling, though the engineering challenges are formidable. You'd need to store compressed gas, release it to space, and capture the cooling effect before the gas disperses. Some spacecraft use sublimating materials for cooling, solid substances that turn directly to gas, absorbing heat in the process. Ice, for instance, sublimes in vacuum, creating a cooling effect. Water's behavior in space reveals another layer of complexity. In vacuum, water doesn't behave like it does at atmospheric pressure. On Earth, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius at sea level. In spaces near vacuum, water can exist in all three states, solid, liquid, gas, simultaneously, depending on temperature and local pressure conditions. A droplet of water released in space would simultaneously freeze on its surface while boiling from its interior. The surface freezes because radiation cooling quickly removes heat. The interior boils because low pressure allows liquid to vaporize at much lower temperatures. This creates bizarre scenarios. Astronauts occasionally report ice crystals forming on their suit's exterior when water vapor escapes. These crystals sublime slowly, turning from solid directly to gas without passing through liquid phase. Meanwhile, any liquid water exposed to vacuum boils furiously, creating gas that instantly disperses. The exact behavior depends on initial temperature. Warm water boils first, then freezes as boiling carries away heat. Cold water might freeze first, then sublime. Either way, free liquid water is unstable in vacuum. These effects matter for life support systems. Spacecraft must carefully manage water recycling. Any leak to vacuum means losing water, and water is precious in space. The ISS recycles urine, sweat, even humidity from breath. Maintaining water in liquid form requires pressure and temperature control. Storage tanks must be sealed, pressurized, and temperature regulated. Otherwise, water escapes as vapor, freezes as ice, or both. The complexity of managing something as basic as water illustrates how fundamentally different space environments are from terrestrial ones. Temperature also affects material properties in ways that matter for construction. Metals behave differently at extreme temperatures. Steel becomes brittle in deep cold, potentially fracturing under stress. Plastics lose flexibility, becoming rigid and crack-prone. Lubricants freeze or evaporate. Electronic components drift out of specification. Batteries lose capacity in cold, overheat in warmth. Every material has optimal temperature ranges, and space pushes many materials outside those ranges. Engineers must either select materials that function across extreme ranges or design active temperature control for sensitive components. The James Webb Space Telescope exemplifies this challenge. Its instruments must operate at incredibly cold temperatures, some below 7 Kelvin, to detect faint infrared signals from distant galaxies. Achieving this requires a massive sun shield, 5 layers of capton and aluminum that block solar radiation while allowing heat to radiate away from the telescope's dark side. The sun shield creates a temperature differential of over 300 degrees Celsius between its sun-facing and space-facing sides. The telescope itself sits behind this shield, passively cooling toward the temperature needed for its infrared detectors to function. No active refrigeration needed, just careful positioning and massive radiation blocking. Compare this to Hubble's Space Telescope, which orbits closer to Earth and operates at warmer temperatures. Hubble detects visible and ultraviolet light, not infrared, so it doesn't need extreme cooling. Instead, it needs temperature stability. Its instruments must maintain consistent temperatures to avoid thermal expansion and contraction that would blur images. Hubble uses heaters, thermostats, and insulation to maintain equilibrium, balancing solar heating against radiative cooling. Different mission requirements demand different thermal strategies. This principle extends to every space mission. Mars rovers must survive Martian nights that drop to -100 degrees Celsius, while functioning in daytime temperatures that might reach 20 degrees Celsius. They use radioisotope heater units, small plutonium-238 capsules that generate steady warmth. They also have insulation, reflective coatings, and thermal switches that adjust heat flow based on conditions. Curiosity and Perseverance rovers can function year-round on Mars, partly because their thermal systems keep electronics and batteries within operational ranges despite extreme environmental swings. Venus missions face opposite challenges. Surface temperatures on Venus exceed 460 degrees Celsius, hot enough to melt lead. Atmospheric pressure is 90 times Earth's. This combination makes Venus incredibly hostile. Soviet Venera landers survived only hours before succumbing to heat and pressure. Modern proposals for Venus exploration include high-temperature electronics that function at extreme temperatures, or elevated platforms that float in Venus's upper atmosphere where conditions are more benign. Temperature drives mission design in ways cold or hot extremes never could on Earth. The Sun itself presents unique thermal challenges. Parker Solar Probe, launched in 2018, approaches within 4 million miles of the Sun's surface, where temperatures exceed 1 million degrees Celsius. How does it survive? A carbon composite heat shield, just 4.5 inches thick, faces the Sun, protecting instruments behind it. The shield reaches temperatures of 1,400 degrees Celsius on its sun-facing surface, while maintaining near room temperature on its shadow side. The probe must carefully orient itself, keeping the shield between Sun and instruments at all times. Deviation means instant destruction. This illustrates the critical importance of geometry in space thermal management. It's not just about materials, it's about positioning, orientation, and exposure. A spacecraft can tolerate extreme temperatures if they're localized and managed. The key is preventing heat from reaching sensitive areas and providing paths for excess heat to escape. Radiators must face cold space. Solar panels must face the sun or be angled to control absorption. Instruments must be shielded or insulated. Every surface becomes part of the thermal management strategy. These lessons from robotic missions inform human spaceflight planning. Long-duration missions to Mars or beyond require life support systems that function reliably across temperature extremes. Habitats must maintain comfortable internal environments regardless of external conditions. Spacesuits must protect astronauts during extravehicular activities where they might encounter temperature swings of hundreds of degrees. All of this requires energy, materials, and engineering solutions that remain reliable over years or decades. The Moon presents specific thermal challenges for future exploration. Lunar surface temperatures swing from 127 degrees Celsius in sunlight to minus 173 degrees Celsius in shadow. Permanently shadowed craters near the poles reach temperatures as low as 33 Kelvin. These regions, never illuminated by sun, are colder than much of deep space because they radiate heat away while receiving none. Conversely, equatorial regions in sunlight become blisteringly hot. Lunar bases must either be built underground for temperature stability or employ sophisticated active thermal control. NASA's Artemis program plans must account for these extremes in habitat design, suit design, and equipment specifications. Consider what this means for the astronauts themselves. Human bodies function within narrow temperature ranges. Core temperature must stay near 37 degrees Celsius. Deviation by just a few degrees causes serious medical problems. Too hot brings heat stroke. Too cold brings hypothermia. Spacesuits must maintain this narrow range despite external temperatures varying by hundreds of degrees. Modern suits use liquid cooling garments, networks of tubes carrying temperature-controlled water worn against the skin. These garments remove metabolic heat, which is then dumped to space through suit radiators. The system must work reliably because failure means death within minutes or hours. Temperature management extends beyond hardware into mission planning. Spacewalks are scheduled considering orbital position, sun angle, and thermal loads. Astronauts avoid extended periods in direct sunlight when possible. They plan activities to minimize exertion during hot periods. They monitor suit temperatures constantly, ready to abort if thermal systems fail. Ground controllers track thermal conditions and advise crew accordingly. What seems simple, maintaining comfortable temperature, requires constant vigilance and multiple backup systems. The longer missions extend, the more critical thermal management becomes. A few hours in a spacesuit is manageable with existing technology. A few days requires more sophisticated systems. Months or years demand completely different approaches. Future missions to Mars will spend 6 months in transit, followed by surface operations lasting over a year. Spacecraft and habitats must maintain stable temperatures throughout without resupply or repair. Redundancy is essential. Single-point failures are unacceptable. Multiple layers of redundancy protect against thermal system failure. Primary systems handle normal operations. Secondary systems activate if primary systems fail. Tertiary backups exist for critical functions. Power systems include redundant generators. Cooling loops have multiple independent circuits. Heaters operate on separate electrical buses. Temperature sensors monitor hundreds of points throughout spacecraft. Computer systems constantly evaluate thermal status and adjust systems automatically. Manual overrides allow crew intervention if needed. This multi-layered approach reflects lessons learned from decades of spaceflight. Early missions experienced thermal failures that cost lives and billions of dollars. Gemini 4 encountered overheating when one astronaut's suit malfunctioned during a spacewalk. Apollo 13 faced life-threatening temperature extremes after the oxygen tank explosion crippled thermal control systems. Astronauts huddled in the lunar module, struggling to stay warm as cabin temperatures dropped toward freezing, while simultaneously managing equipment that risked overheating. Ground controllers improvised solutions using only materials available aboard the spacecraft. The crew survived, barely, but the incident highlighted how quickly thermal problems escalate in space. Modern systems incorporate those hard-won lessons. The International Space Station represents the pinnacle of current thermal management technology. External radiators spanning the length of a football field dissipate waste heat from electronics, life support, and experiments. These radiators must remain precisely oriented relative to Sun and Earth to function optimally. Automated systems track celestial positions and adjust radiator angles continuously. Ammonia flowing through these radiators transfers heat from internal systems to external surfaces, where it radiates away into space. The ammonia loops operate under high pressure and require constant monitoring because leaks would be catastrophic. Internal temperature zones allow different areas to maintain different conditions. Laboratories stay cooler for equipment and experiments. Crew quarters maintain comfortable temperatures for sleeping. Exercise areas accommodate higher temperatures from physical activity. Air circulation systems distribute heat evenly, preventing hot or cold spots. Humidity control removes moisture from breathing and perspiration because excess humidity degrades equipment and creates discomfort. All these systems work together seamlessly, creating a shirt-sleeve environment inside while external surfaces experience temperature extremes. But space stations orbit Earth in relatively benign thermal conditions compared to deep space missions. Planetary exploration ventures far from Sun's warming influence. Temperature challenges multiply with distance. Jupiter receives 25 times less solar energy than Earth. Saturn receives 100 times less. Neptune receives 900 times less. Spacecraft visiting these outer planets cannot rely on solar panels for power because sunlight is too weak. Instead, they use radioisotope thermoelectric generators that convert heat from radioactive decay into electricity. These RTGs also provide warmth to keep instruments above minimum operating temperatures. Voyager probes launched in 1977 still function today because their RTGs provide both power and heat. As plutonium decays, heat output gradually decreases. Engineers carefully manage remaining thermal budget, shutting down non-essential systems to conserve energy for critical instruments. Eventually, perhaps in the 2030s, the probes will cool below operational limits and fall silent. Their longevity testifies to robust thermal design that anticipated decades of operation in the coldest reaches of the solar system. Mars presents unique thermal challenges distinct from either Earth orbit or outer solar system. The planet receives about half the solar energy Earth gets, making it significantly colder. Average surface temperature is -60 degrees Celsius, with winter poles dropping to -125 degrees Celsius. But equatorial regions in summer can reach 20 degrees Celsius during daytime. The thin atmosphere, less than 1% Earth's density, provides minimal insulation. Surface temperatures swing wildly between day and night, sometimes varying by 100 degrees Celsius within hours. Wind patterns create dust storms that block sunlight and alter thermal conditions unpredictably. Mars rovers must survive these conditions while conducting science operations. Spirit, Opportunity, and Curiosity faced similar thermal design challenges despite arriving years apart. Each uses radioactive heaters to keep electronics warm during frigid nights. Each positions instruments and cameras to minimize temperature exposure. Each carefully schedules activities to avoid thermal extremes. Curiosity's RTG provides more heating capacity than Spirit and Opportunity's solar panels, allowing operations during winter months when earlier rovers hibernated. Perseverance, arriving in 2021, builds on these designs with enhanced thermal management, enabling year-round operation at higher latitudes. Future Mars missions face even greater challenges. Human missions require habitats maintaining comfortable temperatures for months or years. Unlike rovers that can hibernate during cold periods, human life support must function continuously. Astronauts need consistent temperatures, humidity control, and air circulation regardless of external conditions. Initial missions might use nuclear reactors for power and heat, but sustained colonization requires systems using local resources. Mars has water ice, carbon dioxide, and minerals that could potentially support fuel production, construction materials, and thermal mass for passive temperature regulation. One concept involves building underground habitats where temperature remains relatively constant year-round. Several meters below the surface, temperature stabilizes around -60 degrees Celsius, regardless of surface conditions. While still cold by Earth standards, this constancy simplifies thermal management compared to surface structures experiencing 100 degrees Celsius daily swings. Heating underground habitats requires less energy than heating surface structures that lose heat to the environment continuously. Radiation shielding improves underground as well, addressing two critical challenges with one solution. Another approach uses thick walls or regolith berms as thermal mass. Large masses heat and cool slowly, damping out rapid temperature changes. A habitat covered with meters of Martian soil would maintain steadier internal temperatures than thin-walled structures. During the day, thermal mass absorbs excess heat. At night, it releases stored heat, moderating temperature extremes. Combined with active heating systems, this passive approach reduces energy requirements and improves reliability. Venus represents the opposite extreme. Surface temperatures reach 465 degrees Celsius, hot enough to melt lead. Atmospheric pressure equals that found 900 meters underwater on Earth. Clouds of sulfuric acid blanket the planet. No spacecraft has survived more than a couple hours on Venus's surface despite heavy insulation and cooling systems. The Soviet Venera probes that briefly transmitted from the surface required extensive thermal protection just to reach the ground intact. their electronics cooked within minutes despite sophisticated cooling. Future Venus missions might use high-temperature electronics and materials developed for jet engines and industrial applications. Some designs propose hovering in the upper atmosphere where conditions are less extreme. At 50 kilometers altitude, Venus's atmosphere has Earth-like pressure and temperature. Floating platforms could conduct long-term observations without facing crushing surface conditions. But even upper atmosphere missions face thermal challenges from solar heating and atmospheric heat rising from below. Mercury, closest planet to the Sun, experiences the most extreme temperature range of any planet. Daytime temperatures reach 430 degrees Celsius, where sun beats down vertically. Night side drops to minus 180 degrees Celsius. The planet rotates slowly, taking 59 Earth days per rotation, so day and night each last weeks. A Mercury lander would experience gradual heating over Mercurian days, followed by gradual cooling during long nights. Surviving requires either highly efficient active cooling during day and heating during night, or possibly mobility to stay in the terminator zone, where temperatures moderate. These planetary examples illustrate how each environment demands unique thermal solutions. No universal approach works everywhere. Engineers must understand local conditions thoroughly and design systems matching specific challenges. Testing becomes critical because mistakes in space are unforgiving. Thermal vacuum chambers on Earth simulate space conditions, allowing engineers to verify designs before launch. Spacecraft undergo extensive testing at temperature extremes, thermal cycling between hot and cold repeatedly, and long-duration thermal balance tests, ensuring all systems function correctly. Despite rigorous testing, unexpected thermal issues occur. Deep Impact Probe encountered anomalies when solar heating exceeded predictions. Mars Climate Orbiter failed partly due to thermal problems during aerobraking. Hubble Space Telescope required multiple servicing missions to replace degraded insulation and failing cooling systems. Each failure teaches lessons that improve subsequent missions, but the learning curve costs billions and sometimes lives. Looking forward, emerging technologies promise better thermal management for future missions. Phase change materials store and release heat at specific temperatures, smoothing out thermal swings without active systems. Aerogel insulation provides better thermal protection with less mass than traditional materials. Advanced radiators using variable emissivity coatings adjust heat rejection automatically based on temperature. Heat pipes using exotic working fluids function across wider temperature ranges than conventional systems. Some concepts propose using superconducting materials that conduct electricity without resistance, eliminating waste heat from electrical systems entirely. Quantum technologies might revolutionize thermal management. Quantum dots could convert waste heat directly into electricity with unprecedented efficiency. Quantum refrigerators might achieve cooling below what conventional systems allow. These remain experimental, but they point toward possibilities decades ahead. As humanity pushes deeper into space, thermal challenges will only intensify. The coldest and hottest environments in the solar system await exploration. Success requires continuing innovation in materials, systems, and strategies. Temperature management isn't glamorous compared to rockets and robots, but it's absolutely fundamental. Without solving thermal challenges, spacecraft cannot function, instruments fail, electronics malfunction, batteries freeze or overheat. Propellants boil away or freeze solid. Structures warp and crack. Every space mission depends on maintaining appropriate temperatures, despite environmental extremes that would quickly destroy unprotected equipment. The next time you see images from Mars or Jupiter or the Sun's surface, remember that sophisticated thermal systems make those observations possible. Engineers working behind the scenes have solved countless challenges to keep those cameras, spectrometers, and transmitters functioning in conditions that would seem impossible. Their work continues pushing boundaries, enabling exploration of increasingly extreme environments where temperature represents just one of many challenges standing between humanity and the cosmos. Human thermal regulation presents unique challenges beyond mechanical systems. Our bodies maintain 37 degrees Celsius through metabolic processes generating constant heat. On Earth, we dump excess warmth through convection, conduction, evaporation, and radiation. Space eliminates the first two entirely. Inside a spacesuit, an astronaut generates 250 watts of heat through basic metabolic activity. During strenuous work like spacewalks, that jumps to 400 watts or more. Without cooling, internal temperature would rise dangerously within minutes. Early spacesuits used simple ventilation systems that proved inadequate. Astronauts overheated quickly during Apollo missions despite engineers' best efforts. The solution came through water-cooled undergarments. Tubes woven throughout the suit circulate chilled water against the skin, absorbing heat directly from the body. This liquid cooling and ventilation garment revolutionized spacewalk capability. The water then flows to a backpack-mounted sublimator that dumps heat into space by freezing and vaporizing water exposed to vacuum. Elegant physics meeting practical engineering. But what about the opposite scenario? What happens when a human encounters space without protection? Hollywood exaggerates dramatically. Movies show instant freezing or explosive decompression. Reality plays out differently, though still deadly. The primary threat isn't temperature at all. It's oxygen deprivation. Within 15 seconds, deoxygenated blood reaches your brain. Unconsciousness follows immediately. You have roughly 90 seconds before death becomes unavoidable. Temperature effects develop more slowly than films suggest. Your body won't freeze instantly because radiation transfers heat gradually. Freezing would take 12 to 26 hours depending on local conditions. You'd die from asphyxiation long before temperature became the issue. Water in tissues would begin boiling at body temperature due to low pressure, causing painful swelling called Ebism. But your skin remains strong enough to prevent actual rupture. One documented case involved a NASA technician in 1966. During spacesuit testing, the chamber accidentally depressurized to near vacuum. The technician remained conscious for about 14 seconds. He later reported hearing air escaping his body and feeling water boil on his tongue. After repressurization, he recovered fully with no lasting damage. This real-world incident confirmed what animal experiments had suggested. Brief vacuum exposure allows survival if recompression happens quickly. The Soyuz 11 tragedy in 1971 demonstrated the fatal outcome when rescue isn't possible. 3 cosmonauts died during re-entry when a valve malfunctioned, depressurizing their capsule. They lost consciousness within seconds. When recovery crews reached them, all 3 appeared to be sleeping peacefully. Autopsy revealed they'd suffocated as atmosphere vented into space. These incidents taught crucial lessons about pressure suit design. Modern suits include multiple redundant seals and automatic emergency systems. Astronauts practice emergency procedures repeatedly. Prevention became the focus because accidents in space leave little room for error. Temperature extremes pose different risks for different body parts. Eyes present particular vulnerability. During Apollo missions, astronauts reported seeing flashes of light with eyes closed. These resulted from cosmic rays passing through their eyeballs, exciting retinal cells. Not temperature-related, but it illustrates how space affects biology in unexpected ways. Temperature-wise, eyes can freeze or overheat faster than other tissues due to high water content and exposure. Extremities face greater risk than the core. Fingers and toes, having less mass and more surface area, lose heat faster. Early spacesuit gloves caused problems with both overheating during work and freezing during rest. Engineers eventually developed electrically heated fingertips, controlled by astronauts via switches. This solved the freezing issue without causing burns. Breathing presents another thermal challenge. Inhaling vacuum would be catastrophic, but even in a pressurized suit, managing air temperature matters. Too cold and moisture in exhaled breath condenses, fogging visors and potentially freezing. Too warm and astronauts become uncomfortable and cognitively impaired. Modern suits maintain breathing air at comfortable temperatures while managing humidity carefully. Now shift perspective from human bodies to the broader universe. What determines temperature in the cosmic void itself? Space has no temperature in the conventional sense, because temperature measures particle motion and space contains almost no particles. But radiation fills the void. The cosmic microwave background bathes everything in 2.7 Kelvin radiation. This represents the cooled remnant of the Big Bang itself, stretched by universal expansion over 13.8 billion years. Originally, the universe was unimaginably hot. Within the first second after the Big Bang, temperatures exceeded trillions of degrees. Particles moved at relativistic speeds. As space expanded, energy density decreased and temperature dropped. After 380,000 years, the universe cooled enough for electrons to bond with protons, forming neutral hydrogen. This moment, called recombination, allowed light to travel freely for the first time. That light, stretched and cooled by expansion, becomes the cosmic microwave background we detect today. Measuring the CMB revealed remarkable uniformity. Temperature varies by only 1 part in 100,000 across the entire sky. Hot spots and cold spots differ by just 0.000018 degrees. This extraordinary smoothness initially puzzled cosmologists. How could regions of space separated by distances larger than light could have traveled since the Big Bang show such similar temperatures? Cosmic inflation theory provided the answer. In the first fraction of a second, space expanded exponentially faster than light speed. This didn't violate relativity because space itself expanded rather than matter moving through space. Inflation stretched tiny quantum fluctuations to cosmic scales, imprinting patterns that evolved into galaxies and galaxy clusters. The CMB's subtle variations map these primordial density differences. Roughly 400 CMB photons occupy every cubic centimeter of space. They pass through us constantly, unnoticed. These ancient photons have traveled since the universe became transparent, carrying information about cosmic conditions nearly 14 billion years ago. Studying them reveals the universe's composition, age, and geometry with remarkable precision. But the CMB represents just one aspect of cosmic temperature. Local conditions vary wildly. Near stars, temperatures soar. In molecular clouds, they plummet to nearly absolute zero. The coldest natural place in the universe exists 5,000 light-years away in the constellation Centaurus. The Boomerang Nebula holds this record at 1 Kelvin, colder even than the CMB. How does anything get colder than the background temperature of space? The answer involves a dying star ejecting material at extraordinary speed. Gas expands so rapidly, it cools through adiabatic expansion faster than radiation from surrounding space can warm it. The central star has expelled nearly 1.5 solar masses over 1,500 years at speeds exceeding 160 kilometers per second. This rate far exceeds typical planetary nebulae. As gas rushes outward, it performs work against its own pressure, removing energy from the system. Temperature drops below even the cosmic background. The Boomerang Nebula essentially acts as a cosmic refrigerator, pumping heat out faster than it comes in. Observations reveal a bow-tie shape created by fierce stellar winds. Material streams outward at 500,000 kilometers per hour, carrying away thermal energy. The process cannot last forever. Eventually, the star will exhaust itself and the nebula will disperse. Surrounding radiation will warm the gas back above the CMB temperature. For now, though, this represents the coldest known natural location in the universe. At the opposite extreme, intergalactic plasma reaches millions of degrees. Between galaxies, diffuse gas maintains temperatures around 2 million Kelvin despite low density. This hot plasma accounts for roughly half of all ordinary matter in the universe, yet remains invisible in optical wavelengths. X-ray telescopes detect it through high-energy photons emitted by superheated particles. How can space contain both 2.7 Kelvin background radiation and 2 million Kelvin plasma? The answer lies in density. The CMB photons vastly outnumber plasma particles. Though plasma particles move at extreme speeds indicating high temperature, so few exist per cubic meter that their total energy remains small. The CMB dominates overall energy density despite its low temperature. This demonstrates how temperature in space differs fundamentally from everyday experience. On Earth, temperature correlates directly with heat content because atmospheric density remains roughly constant. In space, vanishingly low densities mean high temperatures don't necessarily indicate much thermal energy. A handful of particles moving at tremendous speeds can be hot while contributing negligible energy to their surroundings. Interstellar clouds show similar complexity. Dense molecular clouds where stars form maintain temperatures around 10 Kelvin. These cold, dark regions contain mostly molecular hydrogen with dust grains. Stellar radiation barely penetrates their dense cores. They represent some of the coldest environments in the galaxy, though still warmer than the Boomerang Nebula. Less dense clouds reach 100 Kelvin or higher. Ultraviolet radiation from nearby stars heats their gas. These warmer regions appear as glowing nebulae in photographs, ionized hydrogen emitting characteristic red light. The temperature difference between 10 and 100 Kelvin dramatically affects chemistry and physics. Cold clouds allow molecules to form and survive. Warm clouds break molecules apart through energetic collisions. Stars themselves span enormous temperature ranges. Cool red dwarfs maintain surface temperatures around 3,000 Kelvin. Hot blue giants exceed 30,000 Kelvin. The Sun sits in the middle at roughly 5,800 Kelvin. These surface temperatures seem extreme by human standards, but stellar cores reach far higher values. Nuclear fusion in the Sun's core requires 15 million Kelvin. More massive stars need even higher core temperatures to fuse heavier elements. When massive stars exhaust their fuel, core temperatures spike momentarily before collapse. During supernova explosions, temperatures briefly exceed 100 billion Kelvin. At these extremes, normal matter breaks down completely. Protons and electrons merge into neutrons. Exotic particles appear and vanish. The physics governing such conditions pushes beyond current understanding. Recent research suggests the universe overall is warming. Measurements of intergalactic gas show temperatures have increased from around 1 million Kelvin in the early universe to 2 million Kelvin today. Structure formation drives this heating. As matter collapses into galaxies and galaxy clusters, gravitational potential energy converts to thermal energy. Gas falling into dark matter halos heats up before settling into galaxies. This gradual warming seems counterintuitive given universal expansion, but it reflects how gravity organizes matter into increasingly complex structures. While space expands and the CMB cools, localized regions heat up through gravitational collapse. The universe becomes simultaneously colder and hotter depending on where you look and what you measure. Black holes present their own temperature puzzles. Hawking radiation theory predicts black holes emit thermal radiation with temperature inversely proportional to mass. Stellar mass black holes would have temperatures below the CMB, making them effectively colder than space. Supermassive black holes in galaxy centers would be even colder, perhaps billionths of a Kelvin. These predictions remain unverified because Hawking radiation from astrophysical black holes is far too weak to detect. Only microscopic black holes, if they exist, would be hot enough to observe. Such tiny black holes would evaporate rapidly through Hawking radiation, potentially exploding in bursts of gamma rays. None have been detected yet. Temperature in space ultimately reflects energy distribution throughout the universe. From the cosmic microwave background to stellar cores, from frigid molecular clouds to superheated plasma, temperature varies by factors of trillions. Understanding these extremes reveals fundamental physics and the universe's evolution from the Big Bang to today. Human exploration pushes into these temperature extremes gradually. Each mission extends our reach slightly further, testing new technologies against harsher conditions. The knowledge gained enables future missions to go deeper, stay longer, and accomplish more. Temperature management remains central to every advance, determining what's possible and what remains beyond current capability. Future missions face even greater temperature challenges. Mars exploration requires surviving conditions Earth's technology barely handles. Martian surface temperatures range from 20 Celsius during summer days to -153 Celsius at the poles in winter. Daily swings exceed 100 degrees at many locations. Dust storms complicate matters further, coating solar panels and blocking heat radiation. Equipment must function through these cycles for months or years. The Moon presents different obstacles. Lunar nights last 2 Earth weeks. Temperatures plunge to -173 Celsius in permanent shadow craters. Some regions near the poles never see sunlight. These permanently shadowed areas may contain water ice, valuable for future bases, but accessing them requires technology capable of operating in cold approaching absolute zero. Designing systems for such extremes pushes engineering limits. Electronics behave unpredictably at very low temperatures. Semiconductors change properties, batteries lose capacity, lubricants freeze solid, moving parts seize. Every component needs testing and often redesign. Heat also poses serious problems on the Moon. Sunlit areas reach 127 degrees Celsius. Equipment exposed to direct sun absorbs enormous energy. Without atmosphere to disperse heat, components can overheat rapidly. The temperature difference between a crater's sunny rim and shadowed floor might exceed 300 degrees within meters. Future habitats must manage these extremes while keeping humans comfortable. Life support systems need consistent temperatures around 20 degrees Celsius. Creating this stability in such variable conditions requires substantial energy. Solar power works during lunar day but fails during 2-week nights. Nuclear power offers an alternative but adds complexity and risk. Water behavior in space creates unique challenges. In vacuum, water doesn't boil in the normal sense. At low pressure, it simultaneously evaporates and freezes. This process, called sublimation, converts liquid directly to vapor without passing through a proper boiling phase. The vapor escapes, while remaining liquid freezes instantly. This strange behavior has practical implications. If a pressure suit tears and air escapes, any exposed moisture behaves chaotically. Saliva and tears would boil and freeze simultaneously. Your tongue would feel water vapor escaping while ice crystals formed. This sensation reportedly feels like boiling, as one NASA technician who experienced accidental depressurization described. The human body contains roughly 60% water. In vacuum, this water tries desperately to escape. Blood doesn't boil inside veins because blood pressure maintains enough force to prevent it. But water vapor forms throughout tissues. This creates swelling, called Ebism. Your body would roughly double in size within seconds. Skin stretches, but generally holds together. Eyes remain intact despite pressure differential. These effects sound horrific, but they're reversible if repressurization happens quickly. Animal studies show complete recovery from exposures under 90 seconds. Longer exposures cause permanent damage or death. The critical factor isn't temperature, but oxygen deprivation. Your brain loses consciousness after 15 seconds without oxygen. Death follows within 2 minutes. Temperature affects this timeline somewhat. In extreme cold, metabolic processes slow. This might extend survival time slightly, similar to cold water drowning victims who've been revived after extended periods. But the effect isn't dramatic enough to matter practically. Whether space around you measures 3 Kelvin or 300 Kelvin, you'd lose consciousness at roughly the same rate. This reveals something counterintuitive about space. Temperature matters less for immediate survival than you'd expect. Pressure and oxygen dominate short-term concerns. Temperature becomes critical only for extended exposure or equipment operation. Spacecraft design reflects these priorities. Life support focuses first on pressure and atmosphere. Temperature control comes next, but uses relatively simple systems compared to maintaining breathable air. Most spacecraft use radiators to dump excess heat. These work like car radiators, but release thermal energy directly to space through radiation rather than warming air. The International Space Station demonstrates sophisticated thermal management. Its radiators span enormous areas, looking like giant wings extending from the main structure. These panels contain ammonia coolant that absorbs heat from the station's interior. Pumps circulate this coolant to the radiators, where it releases heat as infrared radiation into space. The system maintains comfortable temperatures inside while rejecting waste heat from electronics, human bodies, and sunlight streaming through windows. Without these radiators, the ISS would overheat dangerously. All the equipment generates heat continuously. Solar panels add more thermal energy. The station would quickly become unbearably hot without active cooling. This surprises people who assume space is cold would naturally refrigerate spacecraft. The vacuum provides excellent insulation, trapping heat rather than conducting it away. Future spacecraft heading to distant planets face different thermal challenges. The outer solar system receives much less sunlight. Jupiter gets only 4% of Earth's solar energy. Saturn receives less than 1%. Missions to these worlds must generate their own heat, while using solar panels becomes impractical. Radioisotope thermoelectric generators provide one solution. These devices convert heat from radioactive decay into electricity while also warming the spacecraft. The Voyager probes, now beyond the solar system's edge, still operate using RTGs launched in 1977. Their plutonium cores will generate usable heat for decades more. But RTGs produce only modest power. Future missions may need nuclear reactors for adequate energy. This introduces new thermal challenges. Reactors generate substantial heat requiring careful management. In vacuum, removing this heat requires large radiators. The reactor's extreme temperatures demand special materials and designs. Mars missions present yet another thermal puzzle. The thin atmosphere provides some convection but far less than Earth. Carbon dioxide makes up 95% of Martian air. The atmospheric pressure averages only 600 pascals, less than 1% of Earth's. This wispy atmosphere transfers heat poorly. Equipment must rely primarily on radiation for cooling. Dust storms on Mars create additional complications. Fine particles coat surfaces, changing their thermal properties. Solar panels covered in dust absorb more heat while generating less power. Radiators clogged with dust radiate less efficiently. Cleaning systems add weight and complexity. The Martian day lasts 24.6 hours, close to Earth's. This allows solar power to work reasonably well near the equator. But polar regions experience the same seasonal extremes as Earth's poles. Winter darkness lasts months. Summer provides continuous sun. Temperature swings match these light cycles. Water ice exists beneath the Martian surface at many locations. Extracting and processing this ice requires heating it above freezing. In the Martian environment, this demands significant energy. The ice itself sits at -50 Celsius or colder. Warming it to liquid state, then purifying it for drinking, consumes substantial power. Future Mars bases will likely bury habitats underground. The Martian soil, called regolith, provides insulation against temperature swings. Several meters of regolith maintains relatively stable temperatures year-round. This reduces heating and cooling requirements significantly. Underground construction also offers radiation protection from cosmic rays. But underground building faces its own thermal challenges. Digging through frozen regolith requires heating. Life support systems underground need careful heat management. Without surface radiators, excess heat must be conducted into surrounding soil. This works only if the soil can absorb and disperse the thermal energy adequately. Asteroid mining missions will encounter extreme temperature variations. Most asteroids rotate, creating day-night cycles. Without atmospheres, these cycles produce wild temperature swings. The asteroid Bennu, visited by the OSIRIS-REx mission, experiences surface temperatures from -73 to 77 Celsius. Equipment landing there must handle this 150-degree range. Some asteroids barely rotate. One side perpetually faces the sun, while the other remains in shadow. The temperature difference between these hemispheres can exceed 400 degrees. Landing sites must be chosen carefully. Operating on the daylight side requires cooling systems. Working in permanent shadow needs heating. Comets present even more extreme conditions. Approaching the sun, comets heat rapidly. Their icy surfaces sublimate, creating the characteristic tail. This process absorbs enormous heat, yet shadowed areas remain at deep space temperatures. Equipment on a comet would experience temperature changes of hundreds of degrees as the comet rotates and orbits. Venus exploration faces perhaps the most challenging thermal environment in the solar system. The surface temperature averages 464 Celsius, hot enough to melt lead. This results from a runaway greenhouse effect. The thick carbon dioxide atmosphere traps heat so efficiently that Venus is hotter than Mercury, despite being farther from the Sun. The atmospheric pressure at Venus's surface reaches 92 times Earth's. Combined with the extreme heat, these conditions destroy conventional spacecraft within hours. Soviet Venera probes survived only 23 to 127 minutes on the surface before succumbing. Their electronics cooked, solder melted, seals failed. Future Venus missions require fundamentally different technology. High-temperature electronics using silicon carbide or gallium nitride can function at 500 degrees Celsius. These materials maintain semiconductor properties at temperatures that destroy silicon, but they're expensive and difficult to manufacture. No Venus lander has yet used them. Alternative approaches avoid the surface entirely. Floating stations in Venus's upper atmosphere encounter Earth-like temperatures and pressures. At 50 kilometers altitude, conditions are surprisingly benign. Temperature hovers around 75 Celsius. Pressure equals Earth's surface. A balloon filled with breathable air would float at this level because our air mixture is less dense than Venus's carbon dioxide atmosphere. Such floating stations could study Venus for extended periods. Solar panels would work in the constant sunlight above the clouds. The environment, while acidic from sulfuric acid in the atmosphere, is manageable with proper materials. Several proposed missions explore this concept. Jupiter and Saturn lack solid surfaces. Their atmospheres transition gradually from gas to liquid to metallic hydrogen under extreme pressure. Temperature and pressure both increase with depth. Probes descending into these atmospheres would eventually be crushed and melted simultaneously. The Galileo probe entered Jupiter's atmosphere in 1995. It descended 156 kilometers before being destroyed. During its fall, temperature rose from -113 to 152 Celsius. Pressure increased from near vacuum to 24 times Earth's surface pressure. The probe transmitted data for 58 minutes before its electronics failed. Deeper in Jupiter's atmosphere, conditions become incomprehensible. Pressure reaches millions of atmospheres. Temperature exceeds 10,000 Kelvin. Hydrogen behaves as a metallic liquid. No known materials could survive these extremes. Understanding Jupiter's deep interior requires indirect methods, analyzing gravitational fields and magnetic properties. Europa, Jupiter's moon, presents intriguing possibilities. Its icy surface measures -160 degrees Celsius, but beneath several kilometers of ice may lie a liquid water ocean. Tidal forces from Jupiter's gravity heat Europa's interior, possibly maintaining liquid water. If this ocean exists, it could harbor life. Reaching Europa's ocean requires drilling through kilometers of ice. The surface temperature complicates this enormously. Conventional drilling generates heat through friction, but at -160 degrees Celsius, this heat disperses rapidly into surrounding ice. Drills might freeze solid. New techniques using hot water jets or nuclear-powered melters may be needed. Enceladus, Saturn's moon, actively vents water into space through cracks in its ice. These geysers prove liquid water exists beneath the surface. The water emerging from these vents freezes instantly, creating ice particles that feed Saturn's rings. Missions could sample these particles without landing, analyzing them for signs of life. The outer solar system's extreme cold preserves material from the solar system's formation. Comets and distant objects remain frozen since the sun ignited. Their ice contains unaltered samples of the primordial solar nebula. Studying these objects reveals conditions 4.5 billion years ago, but accessing them requires spacecraft capable of functioning in near absolute zero conditions. Pluto's surface temperature averages 44 Kelvin. Neptune's moon Triton measures 38 Kelvin. The Kuiper belt objects beyond Neptune are colder still. Electronics must work at temperatures where most materials become brittle and many gases freeze solid. The New Horizons mission to Pluto demonstrated technology for these conditions. Its electronics used heaters to maintain operating temperatures. Power came from an RTG, providing steady warmth. The spacecraft's design minimized heat loss through careful insulation. These techniques enable exploration of the solar system's frozen frontier. Looking beyond our solar system, temperature extremes become even more dramatic. Exoplanets discovered around other stars include worlds far hotter than Venus and colder than Pluto. Hot Jupiters orbit so close to their stars that surface temperatures exceed 2,000 degrees Celsius. Rogue planets drifting through interstellar space might approach the cosmic microwave background temperature. Human expansion into space requires solving all these thermal challenges. Each environment demands specialized solutions. No single technology works everywhere. Progress comes incrementally, each mission pushing slightly further, testing new approaches, learning from failures. Temperature management will remain central to space exploration for generations. Every advance depends on protecting equipment and people from conditions ranging from near absolute zero to stellar surface temperatures. Understanding these extremes and engineering solutions to survive them defines the boundary of human capability and determines how far we can reach into the cosmos. The cosmic microwave background pervades everything, setting space's baseline at 2.7 Kelvin. This represents the universe's residual warmth from the Big Bang. Every cubic centimeter contains roughly 400 photons from this ancient radiation. These photons have traveled 13.8 billion years, their wavelength stretched by expanding space. Originally part of the universe's hot infancy, They now manifest as microwave radiation just barely above absolute zero. But this background temperature tells only part of the story. Temperature in space behaves fundamentally differently than on Earth. The concept itself becomes slippery when particles are so sparse. In a true vacuum with no matter, temperature loses meaning entirely. What we measure as space's temperature actually reflects the energy of whatever sparse matter exists there. The interstellar medium contains approximately 1 million particles per cubic meter. For context, Earth's atmosphere at sea level contains about 10 to the 25th power particles per cubic meter. This extreme difference means heat transfer through conduction and convection becomes impossible. Only radiation remains as a mechanism for energy exchange. This creates counterintuitive situations. An object in Earth orbit doesn't experience a single temperature. Its sunlit side might reach 121 degrees Celsius, while its shadowed side plunges to minus 100 degrees Celsius. These extremes exist simultaneously, separated by mere centimeters. The International Space Station faces this challenge constantly. Its solar panels bask in intense radiation while its shadow side approaches deep cold. Engineers design spacecraft with this duality in mind. Surfaces facing the sun require reflective coatings to reject heat. Shadowed areas need insulation to retain it. Heat pipes transport excess warmth from hot zones to cold ones. Radiators positioned strategically dump waste heat into space through thermal radiation. The Moon demonstrates these principles dramatically. Its equator swings from 250 Fahrenheit in sunlight to minus 300 Fahrenheit during lunar night. A 500-degree range with no atmosphere to moderate it. This happens because the Moon rotates slowly, giving each location nearly 2 weeks of continuous sun, followed by 2 weeks of darkness. Without air to distribute heat, each spot heats and cools independently. Mercury experiences similar but more extreme cycles. Being closest to the sun intensifies the effect. Dayside temperatures reach 430 degrees Celsius. Nightside temperatures drop to minus 180 degrees Celsius. The difference exceeds 600 degrees, all because Mercury lacks atmospheric buffering. Interstellar space presents different thermal environments based on local conditions. Dense molecular clouds where stars form can cool to 10 Kelvin. These clouds contain enough matter for gravity to compress gas and dust. As material collapses, it releases gravitational potential energy as heat. But in the cloud's outer regions, shielded from starlight, temperatures approach the cosmic microwave background. Less dense regions of interstellar space might reach 100 Kelvin. Here, occasional starlight warms the sparse gas. Hot, ionized regions around massive stars can exceed 10,000 Kelvin. These bubbles of superhot plasma expand outward from young stars, creating temperature gradients spanning thousands of degrees over relatively short distances. The Boomerang Nebula stands as the universe's coldest known natural object. Located 5,000 light-years away in Centaurus, it measures just 1 Kelvin. This makes it colder than the cosmic microwave background itself. The dying star at its center expels gas at 164 kilometers per second. This rapid expansion causes adiabatic cooling, where gas does work against its own pressure, extracting energy from the system. The process functions like a cosmic refrigerator. Gas expanding this quickly loses thermal energy faster than surrounding radiation can replenish it. The nebula actually absorbs heat from space, maintaining its temperature below the universal background. Over the past 1,500 years, the central star has lost 1.5 solar masses of material. This extraordinary mass loss rate, 10 to 100 times faster than similar objects, enables the extreme cooling. Understanding heat transfer in space requires abandoning terrestrial intuitions. On Earth, air conducts heat from warm objects. Your body loses heat primarily through conduction to surrounding air and convection as that air circulates. In space, neither mechanism functions, only radiation remains. This explains why movies get space exposure wrong. An unprotected human wouldn't freeze instantly. Your body radiates heat slowly. Freezing takes 12 to 26 hours, depending on local conditions. The immediate danger isn't temperature, but vacuum. Within 9 to 12 seconds, oxygen-depleted blood reaches your brain, causing unconsciousness. Water in tissues begins vaporizing, creating swelling. This condition, called Ebism, occurs because vacuum lowers water's boiling point. Liquid water in your bloodstream and soft tissues transitions to vapor. Your skin's strength prevents explosive decompression, but bubbles form in major veins, blocking circulation. After 1 minute, circulation effectively stops. Oxygen deprivation proves fatal within 90 seconds unless recompression occurs. Studies using dogs and chimpanzees demonstrated that exposure under 90 seconds allows complete recovery. Beyond that threshold, survival becomes unlikely. The 1966 NASA test accident provided grim validation. A technician testing a spacesuit experienced chamber decompression. He regained consciousness afterward, describing hearing air escape from his body and feeling water boil on his tongue. He survived because recompression occurred within the critical window. The 3 cosmonauts aboard Soyuz 11 weren't as fortunate. In 1971, their spacecraft decompressed during re-entry while still in space. When the recovery team arrived, all 3 appeared to be sleeping. They had died from vacuum exposure, the only humans confirmed killed this way. Modern spacesuits represent engineering marvels designed to maintain survivable conditions. They must function across a 500-degree range, from -156 Celsius to 121 Celsius. 14 layers of specialized materials provide this protection. 7 layers of aluminized mylar insulation maintain stable internal temperature, regardless of external conditions. The outermost layer combines Gore-Tex, Kevlar, and Nomex in white ortho fabric. This material withstands temperatures from -180 to 150 Celsius, while resisting micrometeorite impacts. Beneath this, a pressure bladder maintains atmospheric pressure. A restraint layer prevents the bladder from ballooning. The innermost layer, called the liquid cooling and ventilation garment, consists of spandex-like material with embedded cooling tubes. Water circulates through these tubes, absorbing body heat. This system dumps heat into space through an external radiator on the suit's life support pack. Without active cooling, the suit's insulation would cause overheating within minutes. This multi-layer approach mirrors how spacecraft manage thermal extremes. No single solution works everywhere. Each environment demands specific strategies. The key lies in controlling heat flow, either retaining or rejecting it as needed. The universe's warming trend adds another dimension to this story. Research from Ohio State University found that intergalactic plasma reaches 2 million Kelvin. This refers not to empty space, but to the diffuse gas between galaxies. This plasma accounts for roughly half the universe's ordinary matter. These hot regions coexist with the cold cosmic microwave background. The universe contains both simultaneously. Understanding this diversity matters for future exploration. Missions targeting different destinations face vastly different thermal challenges. Europa, Jupiter's moon, presents intriguing possibilities alongside formidable obstacles. Its surface temperature averages minus 160 degrees Celsius, but beneath several kilometers of ice, tidal heating from Jupiter may maintain liquid water. If this ocean exists, it could harbor life. Reaching it requires drilling through ice at temperatures where conventional equipment fails. Drills generate heat through friction, but at minus 160 degrees Celsius, this heat dissipates rapidly. Bits freeze solid. New approaches using hot water jets or nuclear-powered melters might work. Testing these technologies in Earth's Arctic and Antarctic regions provides essential validation. Enceladus, Saturn's moon, actively vents water into space. These geysers prove liquid water exists beneath its icy crust. The ejected water freezes instantly, creating ice particles that feed Saturn's rings. Missions could sample these particles without landing, analyzing them for life's chemical signatures. The outer solar system's extreme cold preserves primordial material. Comets and Kuiper belt objects remain frozen since the solar system's formation. Their ice contains unaltered samples from the primordial solar nebula. Studying them reveals conditions 4.5 billion years ago. Pluto's surface measures 44 Kelvin. Triton, Neptune's moon, reaches 38 Kelvin. Kuiper belt objects beyond Neptune are colder still. Electronics must function at temperatures where most materials become brittle and many gases freeze solid. New Horizons demonstrated necessary technologies. Its electronics used heaters powered by a radioisotope thermoelectric generator. This device converts radioactive decay heat into electricity, providing steady warmth. Careful insulation minimized heat loss. These techniques enable exploration of the solar system's frozen frontier. Beyond our solar system, exoplanets display even more extreme temperatures. Hot Jupiters orbiting close to their stars exceed 2,000 degrees Celsius. Rogue planets drifting through interstellar space might approach cosmic background temperature. Each represents unique challenges for future probes. Human expansion into space demands solving all these thermal puzzles. Each environment requires specialized solutions. No universal answer exists. Progress comes incrementally, each mission testing new approaches, learning from successes and failures. Temperature management remains central to space exploration. Every advance depends on protecting equipment and people from conditions spanning absolute zero to stellar surfaces. Engineering solutions to these extremes determines how far humanity can reach. The universe presents a thermal landscape of extraordinary diversity. From the Boomerang Nebula's single Kelvin to stellar cores burning at millions of degrees, reality spans this entire range. Understanding these extremes reveals fundamental physics and enables practical exploration. Space isn't simply cold. It's thermally complex, with conditions varying by location, proximity to energy sources, and local matter density. This complexity challenges our intuitions, but rewards careful study. Each discovery opens new possibilities while revealing new obstacles. Future missions will push into increasingly extreme environments, Some will seek the coldest regions, hoping to detect subtle quantum effects. Others will approach the sun's corona, sampling plasma at millions of degrees. Both require thermal management solutions at the edge of physical possibility. The cosmic microwave background provides our reference point. At 2.7 Kelvin, it sets the universe's baseline. Everything else represents local variation from this standard. Understanding why and how these variations occur illuminates fundamental processes shaping cosmic evolution. Temperature in space isn't what movies suggest. It's not uniformly cold or instantly lethal. It's nuanced, complex, and deeply connected to the universe's structure and history. Grasping this complexity transforms how we approach space exploration and deepens appreciation for the cosmos we inhabit. Human survival beyond Earth depends on mastering these thermal challenges. From spacesuits to habitats to interplanetary vessels, every system must manage heat transfer without atmospheric assistance. This constraint shapes mission design more than any other single factor. As exploration expands, thermal engineering will advance accordingly. New materials, active systems, and innovative designs will emerge. Each generation of technology will enable missions previously impossible. The boundary between achievable and impossible will shift steadily outward. Temperature defines what's possible in space. It determines where we can send probes, how long they can function, and whether humans can visit. Understanding and overcoming these limitations marks the difference between staying home and reaching the stars. The universe's temperature story isn't what science fiction taught us. Space doesn't freeze you instantly. It doesn't boil your blood in seconds. Reality operates on different rules entirely. That baseline of 2.7 Kelvin represents ancient light, stretched across 13.8 billion years. The cosmic microwave background bathes everything in this faint warmth, a fossil glow from creation itself. But this number masks extraordinary complexity. Temperature in space behaves unlike temperature on Earth because the fundamental mechanisms differ. Without atmosphere, conduction and convection vanish. Only radiation remains. Heat moves slowly, creating situations impossible in terrestrial environments. The International Space Station demonstrates this daily. One surface bakes at 260 degrees Celsius, while meters away, another freezes at -100 degrees Celsius. These extremes coexist because vacuum insulates rather than conducts. Engineers design every spacecraft component accounting for this strange reality. Human bodies generate 100 watts continuously. On Earth, air carries this warmth away effortlessly. In space, that same heat has nowhere to go except through slow radiative loss. Spacesuits require active cooling systems, not because space is hot, but because vacuum traps metabolic heat inside insulation layers designed to protect against external extremes. The Boomerang Nebula proves natural processes can achieve temperatures colder than space itself. At 1 Kelvin, it absorbs heat from surrounding cosmic background radiation. This dying star's rapid gas ejection creates adiabatic cooling faster than radiation can compensate, a cosmic refrigerator operating 5,000 light-years away. Meanwhile, intergalactic plasma reaches 2 million Kelvin. These superheated particles coexist with the cold background because density remains so low. Temperature measures particle speed, not total energy. Fast-moving particles separated by cubic meters contribute little thermal energy despite their extreme velocities. Mars presents unique challenges for exploration. Surface temperatures swing 100 degrees daily. Thin atmosphere provides minimal moderation. Future habitats must maintain comfortable conditions through active systems or underground construction, leveraging thermal mass. Water ice exists beneath the surface, but extracting it requires heating frozen regolith with precious energy. Venus demonstrates the opposite extreme. Surface temperatures of 464 degrees Celsius combined with crushing atmospheric pressure destroy conventional spacecraft within hours. Future missions may avoid the surface entirely, floating in upper atmosphere where conditions become surprisingly Earth-like at 50 kilometers altitude. Europa and Enceladus hint at liquid water beneath icy crusts. Tidal heating from giant planets maintains these hidden oceans, despite surface temperatures far below freezing. Reaching them demands drilling technology that functions at -160 degrees Celsius, where conventional equipment fails as rapidly as heat dissipates into surrounding ice. The outer solar system's frozen worlds preserve primordial material unchanged since the Sun's formation. Pluto at 44 Kelvin, Triton at 38 Kelvin, Kuiper belt objects colder still. Electronics must operate at temperatures where materials become brittle and gases freeze solid. Radioisotope generators provide both power and warmth for missions venturing into these regions. Temperature management drives spacecraft design more than any other factor. Every watt of electrical power eventually becomes waste heat. Solar panels generate electricity, but also collect thermal energy. Life support systems create continuous heat loads. All of this must be rejected into space through radiators, since convection and conduction don't function. The challenge intensifies with distance from the Sun. At Jupiter, solar energy drops to 4% of Earth's intensity. At Saturn, less than 1%. Missions to outer planets require nuclear power sources because solar panels become impractical. These systems generate their own thermal challenges, requiring careful management. Human bodies demand narrow temperature ranges. Core temperature must stay near 37 degrees Celsius. Deviation by just a few degrees causes serious medical problems. Spacesuits maintain this stability across 500-degree external swings through multiple insulation layers, active cooling systems, and careful thermal control. The reality of vacuum exposure differs dramatically from Hollywood depictions. You wouldn't freeze instantly because radiative heat transfer happens slowly. Freezing takes 12 to 26 hours. The immediate threat isn't temperature at all, it's oxygen deprivation. Unconsciousness occurs within 15 seconds. Death follows within 90 seconds unless recompression happens quickly. Water in tissues begins vaporizing due to low pressure, creating painful swelling, but skin strength prevents explosive decompression. The 1966 NASA accident proved brief exposures allow complete recovery. The Soyuz 11 tragedy demonstrated that without rapid rescue, vacuum exposure proves fatal through asphyxiation long before temperature becomes relevant. Understanding these realities changes how we approach space exploration. Temperature extremes matter, but they're manageable with proper engineering. The actual hazards prove more nuanced than simple narratives suggest. Pressure loss threatens immediately. Radiation accumulates long-term cancer risk. Microgravity causes bone density loss and muscle atrophy. Future missions will push into increasingly extreme thermal environments. Some will target the coldest regions, studying quantum effects near absolute zero. Others will approach the sun's corona, sampling million-degree plasma. Both require thermal management at the edge of physical possibility. Each environment demands specialized solutions. No universal approach works everywhere. Progress comes incrementally through testing new technologies, learning from failures, and gradually expanding capabilities. The boundary between possible and impossible shifts steadily outward. The universe presents extraordinary thermal diversity. From the Boomerang Nebula's single Kelvin to stellar cores burning at millions of degrees, reality spans this entire range. Local conditions vary wildly based on proximity to stars, matter density, and complex physics governing energy exchange. This complexity challenges intuition but rewards careful study. The cosmic microwave background provides our reference point at 2.7 Kelvin. Everything else represents local variation from this baseline. Understanding these variations illuminates fundamental processes shaping cosmic evolution. Space isn't uniformly cold. It's thermally complex, with hot and cold regions coexisting because vacuum prevents their mixing. Temperature itself behaves differently when conduction and convection vanish. Heat becomes trapped or radiated slowly, rather than flowing freely through conducting media. Grasping this transforms how we design spacecraft and plan missions. Every system must account for heat transfer limitations. Radiators become as critical as solar panels. Insulation determines what's possible as much as propulsion or power generation. Human expansion beyond Earth depends entirely on mastering these thermal challenges. From spacesuits to habitats to interplanetary vessels, managing heat without atmospheric assistance shapes every design choice. This constraint matters more than any other single factor. As technology advances, thermal engineering will enable previously impossible missions. New materials, active systems, and innovative designs will emerge. Each generation will push further into extreme environments, whether frigid or scorching. The story of space temperature reveals how profoundly different conditions are beyond our atmosphere. It challenges assumptions about hot and cold, forces us to abandon terrestrial intuitions, and demands we understand thermodynamics at its most fundamental level. Every photon from the cosmic microwave background carries information about the universe's infancy. Every temperature measurement reveals something about local conditions and the processes shaping them. From dying stars to forming planets, thermal signatures tell stories about cosmic evolution. Space isn't empty void at uniform temperature. It's a dynamic environment where ancient radiation mingles with hot plasma, where frozen worlds orbit in darkness, where stellar furnaces rage, and where the physics of heat transfer operates by rules we're still learning to navigate. Understanding these truths prepares us for the challenges ahead. As humanity reaches deeper into the cosmos, temperature management will remain central to every advance. It defines what's achievable, determines where we can go, and shapes how we survive in environments never meant for human presence. The terrifying truth about how cold space really is turns out to be far more complex than a single number. It's a story about the nature of heat itself, about how energy moves through vacuum, about the strange physics governing the void between stars. Space isn't just cold or hot. It's both simultaneously, neither uniformly, and always more nuanced than simple descriptions suggest. This understanding matters because it's the foundation for everything that follows. Every habitat, every spacesuit, every probe sent to distant worlds builds on these principles. Temperature isn't an obstacle to overcome once and forget. It's a constant consideration shaping mission design from conception through execution. The universe offers environments spanning absolute zero to stellar infernos. We've barely begun exploring this range. Each new mission ventures slightly further, tests new limits, and expands what's possible. The thermal challenges will intensify as ambitions grow, demanding continuous innovation in materials, systems, and strategies. What seemed impossible decades ago becomes routine through persistent engineering. What seems impossible now may become standard practice within our lifetimes. The boundary keeps moving because we keep pushing it, learning from each attempt, incorporating lessons into better designs. Space temperature isn't what movies show. It's not instantly lethal freezing or boiling. It's a complex landscape of thermal extremes that require careful navigation but don't prevent exploration. Understanding this reality replaces fear with knowledge, transforms obstacles into engineering problems, and converts the unknown into the achievable. Every spacecraft orbiting Earth, every probe exploring distant worlds, every astronaut working outside the space station demonstrates mastery over these challenges. They prove that while space operates by different rules, those rules can be understood, anticipated, and accommodated. The cosmic microwave background will continue bathing the universe in its 2.7 Kelvin glow for trillions of years. Local variations will persist, driven by stars, planets, and the complex physics of matter and energy. And humanity will continue pushing into these extremes, protected by increasingly sophisticated technology built on ever-deepening understanding. Temperature in space represents both barrier and invitation. It limits what's currently possible, while beckoning us to develop solutions enabling tomorrow's achievements. Each thermal challenge overcome opens new destinations, new possibilities, new horizons for exploration. The universe's temperature story continues unfolding. New discoveries reveal unexpected phenomena. New missions encounter conditions we've never tested. New technologies emerge from attempts to solve seemingly impossible problems. This cycle of discovery and innovation drives progress toward futures we're only beginning to imagine. Space isn't uniformly cold, instantly deadly, or impossibly hostile. It's thermally complex, physically challenging, and absolutely explorable with proper preparation. Understanding these truths transforms cosmic exploration from science fiction fantasy into engineering reality, one carefully managed thermal system at a time.